Welcome to this tutorial. We are going to look at this machine, this orienting machine. Let's dive right in. So we have this mechanism down here, a revolving mechanism that drives the escalator. It is transporting some screws or bolts. The bolts then enter a linear feeder, a linear vibratory feeder. And the goal is that they will come out like this on a orderly straight line like that. But what happens is this. They get stuck, the system is like clogged up. And this happens pretty quickly. So it is evident that this is not a dependable design and solution at this stage. So let's see if we can do something about that. Redesign this machine so that it works dependably, so that we can start using it in our production line and trust that it's not going to interfere with our production system. First of all, I just want to say a couple of things about the setup that I have here. We're obviously using Algoryx Momentum to run these simulations. I'm running the simulations on a laptop. The fan will make some noise occasionally. I hope that's not gonna be picked up too much by my microphone. Some settings here. So the simulation frequency, the inverse of the time step, is set to 300 Hertz. I believe it gives us a quite good balance between simulation performance and simulation accuracy. We want to have a balance where we can iterate quickly with our design, but without compromising the stability and accuracy of the simulations too much. So I hope that this is a reasonable level at this stage in the development of this solution. Later on, as we progress, as we hopefully approach a final solution that works really well, we are going to ramp up the simulation frequency to achieve more precise results that would transfer even better to reality when the time comes. Yeah, let's take another look at the simulation here. It looks pretty promising in the beginning. The first few bolts are going through very nicely. We have this guide here that pushes the misoriented ones off the track and back into the bin. And that's what we want. But here, some issue arises and we get blockage. Let's take a closer look at this situation here. Let's see where it occurs. And I'm gonna reduce the playback speed a little bit as well. So maybe 25%, maybe that's a good balance, so we can see what happens. I think it's still running by a little too quickly for me to spot what is happening here. Let's say 1%. Okay, so I can't simulate it like super slowly because the recording frequency that it shows is only 30 Hertz. So that's I need to respect that frame rate that we have available. Okay, there was some some issue there. I think it's this screw here that will get stuck, and we also have some obstructions here. And this bolt right here is definitely not doing very well. We can see that there's a bit of overlap here between the geometries, and that has to do with the simulation frequency that I chose. So it's if I ramp up the simulation frequency, then we wouldn't see this kind of non-physical overlap. But clearly what is happening here is that this first bolt is kind of obstructing the flow, and things starts to pile up here. We need to find some way to stop this from happening. And we have to be a little creative about this. I mean, imagine how you would approach this. Normally, you would probably maybe build another prototype, maybe replace this guide here with a different geometry. Maybe it would take some time to manufacture that new component and install it in the machine. You would then run some new tests to make sure that it works dependably. But that's not the approach that we take here. I'm zooming out a little bit, thinking, trying to be creative here. I think one good step forward is to make it as easy as possible for the misoriented bolts to get this far in the process. And one thing I can do is to grab this component and just move it further back. Another thing that I think we could do that's not gonna cause any new problems, hopefully, and probably wouldn't cost us very much to do either, is to extend this slope here to make it possible for the bolts to fall off on either side of the linear feeder. Let's see if we can do it this way. So I'm just pulling out that surface there. Okay, maybe it doesn't look like, a candidate for a final design, but I'm just trying to iterate quickly here. Experimenting. This is truly a process of trial and error. There are so many things that can go wrong in this type of machine, and eventually all of the bad things that can happen will happen, and it's like an incredibly complex game of chess in a way. It's really difficult to predict all the things that can happen, and when you make a modification to the system, it opens up for a whole new, an entire slew of new possible failure modes. And we can't sit down and try to predict all of them in our heads. Instead, we use simulations. I can provide some insights for free. That's a bad situation right there. That end there, the heads get stuck and get caught on it. I'm gonna fix that right away. I'll just extend further this way. And maybe remove that surface. Can I do that? Yes, I can. I'm just going to pull it all the way down to that surface. There, so it's a bit cleaner now. One thing that I don't like so much here is this one, for example. It clearly doesn't fit. It doesn't have the correct placement, so it should be recirculated as quickly as possible. Just get it out of the way. And how do we do that? Like the one I'm talking about, maybe you remember, it was standing on top of its head, just traveling on this surface. I want it to fall down as quickly as possible. So one thing I can do that would affect this one as well, and possibly also this one and this one and this one. The thing I'm thinking of is just narrowing the surface. So I'll do that, and I'm just going to assume that it's not too difficult to manufacture this shape that I'm aiming for. And I'm going to edit both sides simultaneously. What else do I want to do? I want to make it pretty much as slim as possible. Grab both of those surfaces and move it 2 millimeters that way. Same thing on this side. And now we have that gap there between the ramp and the feeder. Let's close that gap. I'll move this one along as well. I'm going to change the home view here so that we can more effortlessly go back to, let's say, this view. Set as home view. Great. And simulate. Let's see if this one falls off right away now. Yes, nice. That one too. So we're definitely making more room for the ones that are correctly oriented. That one is still an issue. And those ones remain there. We could add some rounds here. Oops. Let's say 2 millimeters. And I have another idea that I want to experiment with. Let's get back to it. I'm just gonna try this design again. Nice. And we have that situation again, which is problematic. I wish that it could just have fallen off sooner. That one's gonna come down on that side. Nice. This doesn't look promising. Nope. I want something that I want to do something that will like help these ones fall off sooner. What can I do? I mean, let's go back again. So we see that they're lined up like this incorrectly. They must be recycled basically. And they are somewhat resting on this surface. When they come off the surface, they just kind of stay where they are, or they continue on the linear feeder. What if we just disturb them a little bit more, so to increase the probability of them falling down? I think what I'll do is this. First, I'm just gonna move this surface up a little bit, like so. I don't know exactly how this is going to be attached to its surroundings. I mean, that's a separate problem. I think we don't really need to address it here. And I want to take See if I can get a good angle here. Just grab all of these items. And I'll move them down a bit. The idea here is that, let's say I move them down 3 millimeters. I want the bolts to be a little, you know, the ones that are incorrectly oriented here. I want them to have a little extra, you know, potential energy when they get off the ramp, so that potential energy will then cause them to fall off the feeder more easily. Let's take a look at that. If we just rotate a little bit, we get a better sense of what's going on. But I kind of like this. Oops, it's not at all what I wanted. So it's difficult to see from this perspective, but the bolts are now moving toward us out of the screen. And we see that when they come off the ramp, they almost like tip over, but not completely. So I think it was that modification that we made. Maybe there's something to it. I think it took us in a good direction. Let's see if we can just take that a little bit further. Move it down 1 more millimeter. And I mean, it would be nice if this wall was even slimmer. Let's see what the thickness is. It's 2 millimeters thick. Let's reduce that by 0.5 millimeter. Come on. And another simulation. That's an interesting looking one. The one right here. And yes, it came off. That was nice. I think this one will come off to the left, and this one hopefully will come off to the right. That one didn't quite make it all the way. Oops. That wasn't perfect. These ones get stuck there. Okay. It works better and better. I wouldn't say that this is a dependable, reliable solution. We certainly have to do something about this. Let's do that right away. And there's one thing that I'm thinking about here. There's a bit of play here, which might be a really, really good thing. But if we allow ourselves to reduce it a little bit, then maybe it would be more likely that the ones that we've been talking about, that they will more easily tip over the edge there. So let's do a couple of modifications to this piece here. First of all, I'm going to pull this surface upward. And then also select this one and move them further up. And I wanted to make this a bit narrower. So how about 0.3? I'm kind of playing with some really slim parameters here, and that's not really how I want to do it. I'd rather come up with a really solid principle on how to achieve a robust solution here. So I don't know, I'm not entirely happy about that modification. Well, that was interesting. Obviously, it would fall down a bit and then land at the bottom there. I'm not sure what I think about that. Maybe it's not entirely bad, but I don't want to introduce that new dimension to this model without having thought through what the implications are. So I think I'll change that again. But what we can see anyway is that they're falling off to the sides more reliably now than before. That is really good. That's a little excessive. I think maybe 1 millimeter should suffice. The fan on my laptop is working hard right now. I hope it's not louder than my voice. I hope it doesn't bug you too much. Nice. Okay, so let's go back to that home view that we created before, like so. Okay, so we're now 17 seconds into production here. And it looks good so far. I bet that something bad will happen soon. I would be surprised otherwise. I mean, these systems, they always have something up their sleeve, something that you hadn't thought of, something that can go wrong. Well, so far so good. And it looks like we'll have a pretty good balance between incoming bolts. We see that there's a stream of incoming bolts coming from the source right here. This little cloud of dots there. So there seems to be maybe an adequate balance between the inflow and outflow. We'll see. I think we have to run the simulation much longer to verify that that we have like a stable equilibrium here. If it starts to get more crowded, then that's gonna impact the performance of the machine. It'll be more crowded here and here and here as well, and that could interfere with how this machine works. And it can cause like an escalating problem. It becomes less efficient, and it starts to like overflow even more until it becomes very evident that it doesn't work. I see that it's almost time for lunch, or it literally is time for lunch. And I think what I'll do is to just leave this simulation running while I'm off having a snack. Oops. And hope that it is still in good order when I come back. Okay, I'm back. I didn't actually finish my lunch yet. I heated up a pie in the micro, and it's too hot, and I'm too curious to see how this is going, so I'm back. And I'm almost surprised to see that it hasn't clogged up yet. That's good, but I think it's overflowing a little bit. I have quite a few bolts here in the tray. Let's see if we can do something about that. Because even if there's a slight imbalance, so we have a slight accumulation that is consistent over time, then eventually is going to become a serious problem and begin to really escalate. So what can we do to fix this? Well, we could reduce the inflow of bolts, but I think it's better to try to improve the throughput of the machine. One simple thing that I'm going to try to do is to just increase the speed of this motor here. So let's say 220 degrees per second. I'm going to leave the torque limits the way they are. If this continues to look promising for a while longer, I'm gonna assume that we have that's not good at all. And maybe that's been happening all this time. But we had an obstruction that was able to make it through anyway because we use a low simulation frequency. Let's let it work a little longer before we go back. And yeah, here's another problem. I'm gonna stop it there and reduce the playback speed. Step forward a little bit. And try to get a better sense of... It's too fast. I should increase the recording frequency so that we can play things back even slower. Okay, so it is sitting like that. That's a mode that we don't really want ever. Like, so this bolt here, I think it looks good now that this is very likely to just fall straight off the feeder when it gets to that point. On the other side over here, we don't have that same mechanism in place. I'm stepping back in the sequence here to get a sense of how it ended up in that position in the first place. So this is an interesting mode right there. Although these two bolts are supporting each other in this unwanted placement. Step forward. And then this head is going to collide with that guide, I suppose, and the pair will begin to turn. It actually didn't happen that way at all. Neither of the bolts have touched the guide yet. They fell into this kind of resting position anyway, and this bolt is just going to find its right orientation, and this one will get trapped like that. And once in this position, it gets some support from this surface. Maybe if I move this surface over to the side, it would have come down automatically. We can try that, and if that issue seems to reoccur, then maybe we have to come up with something else. And let's see if I can just pull that up to this edge. Yes. Back to home view. I'm taking a bite of my pie. Sorry about that. Hope you don't think it's rude. It's a taco pie. It's okay. Not fabulous, but it will do. Another unusual combination. Nice. It almost fell outside of the tray there, so that's something we should fix. Just close that gap. Should be an easy thing to do. These two are they have a placement that is similar to what we had before. It would cause that problem, but they're not interlocking as much. My goal up to this point has been to achieve a solution that is reliable, that's not going to fail. But as you can see, whoops, that one came outside. As you can see, a lot of these bolts are recirculated back into the bin. And that's not particularly efficient. If we had no recirculation whatsoever, if all bolts just were able to line up perfectly, I think the throughput of this machine would probably more than double. I don't think that I will attempt to make that happen in this tutorial. Maybe that's a topic for another video. And there are a couple of things that I'm thinking might be a topic for another video, or multiple other videos. I don't know. It depends on what you want, I guess. So one would be to not only achieve a reliable, dependable design, but one that has a much better throughput than what we have here at this point. Another topic might be to to verify more thoroughly that the design that we arrive at, that it actually works as well as we think. I mean, what I've been trying to do now is just to iterate quickly, have a workflow in place where I can be creative and discover as many issues as possible with this design, and creatively, with a bit of reasoning, arrive at this seemingly apparently dependable design, right? But before we push the button and order this machine from the workshop, we want to feel more certain that it actually will work as predicted under a range of different circumstances, different levels of friction, for example, maybe some slight variations in the shape of these bolts. It might be interesting we should definitely talk to like the production team as well, to get their input on this design. Is it a good design for production? Maybe they would have a really hard time creating this linear feeder with this shape that we have in the simulation. So it would be really interesting or important to get their feedback on that. I'm going to stop the simulation there and just adjust a couple of things that I noticed. I want to just close this gap a little bit, and I'll just pull it out to line up with this surface over there, and same thing there. I mean, there are other things that I could do as well, but I think this is good enough for our purposes here. So anyway, if you want me or us to dive deeper into other aspects about this particular machine, let us know. We're very happy to talk about this with you and hear your input, learn from your expertise. And also, if you have recommendations for other machines, please let us know. So machines that I'm thinking of are bowl feeders, for example, and also other like vibratory feeders. But I think primarily bowl feeders. They're really interesting and valuable machines. Also conveyor systems of various types. With that, thank you very much for sticking with me this long. Bye.